these days programs run together, share object memory cache, the same way that cars share the streets. So a while ago, I had this idea asking my student Bing that maybe it's a good idea for drivers to be defensive. Maybe it's time to let programs be defensive. So that's about my contribution to this work. So Bing really did real work, but because of that, he graduated. I can't pay him to come to the conference, and his employer has a different priority, so you have me. As the usual advisor giving the talk, I'll stay at the high level. Actually, literally. This is a slide from Bimbo's thesis defense. It's actually from another former Russian graduate when he came back to give a seminar talk. And then the question Shipeng asked was, what's the difference between a program and a bird? And the answer is that the bird can learn to fly back every time it tries, but program still can't do that. And then a lot of work has been done in this area. In the new problem of shared resources, so we actually have programs, it's analogous to birds, need to learn to fly, not just better by itself, but also learn to fly with peers. And then there are different types of interaction. So Bing's thesis is actually peer-aware program optimization. So they're interfering interactions. So when there are only limited resources, we see we have to fight for it, and then there is contention. The other one is as in parallel code, then different tasks can actually collaborate. So that's what's really happening on modern processors. So looking at the current session, a lot of exciting work coming out, and a number of them from previous CGO conferences. People look at different strategies. So our focus is actually looking at compiler optimization. And do we need to rethink compiler optimization, keeping in mind that the program is going to run with other programs? And a very nice case to study is loop tiling, because here we have a compiler that can change the working set of the program to very precise sizes. This is known as tile sizes. Right? When I have the matrices and when I tile it, I can decide how much each tile is. And in this way, I decide how much data I'm reusing in cache. So this is a great vehicle to study cache sharing and the effect of compiler optimization, because compiler can control the size of the data in cache. And then we sort of curious what will happen if we sort of adjust the control. And in matrix multiply, this probably everybody knows, the way loop tiling is to change the original 3-dimensional loop into a 6-dimensional loop, and then the inner 3 dimensions are the tiled loops, and then the tile sizes are determined by these blocking factors, so bj, bk. And then just by changing those, we change the footprint in cache. So what do you think is the right way? If we tile for the whole cache, that's inconsiderate, so that's certainly not a good idea. But if we tile for part of the shared cache, then the question is how much? Since we don't know who this program is going to run with, so that's hard to determine. And a safe strategy, we thought, so at least I thought, is that we can tile for private cache. So in that case, we don't really have to rely on cache sharing. But Bing told me that's not the case, because there's a problem called inclusion victim misses. And on x86 processors, AMD actually does things differently, but on x86 processors, the cache hierarchy is inclusive. That means everything we have in private cache, we have to have a copy in shared cache. So the content of the private cache L2 has to be part of the content of L3. if it occurs that a data block has to be evicted from the shared cache on x86, because the inclusion property, that data has to be evicted from the upper level cache as well. So that's causing the miss that's called inclusion victim miss. So here is a toy example. I have two programs. I have a really small shared cache, size 8. And then for these two programs, the first program just use one data element, A, so it fits perfectly in the private cache. But then the other program is sort of streaming through data larger than the cache size. And then because of the good locality in private cache by program 1 actually, once it loads A into private cache, it doesn't touch the data in the shared cache. So it becomes code. It's paradoxical. You have hot data actually become code. Because it's hot, it's code in the shared cache, and then will be evicted by the other program because it's actively accessing data, loading it into shared cache. And then every once in a while, it will evict A from the shared cache, causing inclusion victim miss. So we see these misses. The first time is called start miss, and then after that, it's going to be inclusion victim misses. So that's a problem for the toy example. What about real programs? So let me quickly go to the data that started being studied. He actually simulated matrix multiply using a cache simulator with realistic cache sizes 256 kilobytes, level 1 private cache, and then 2 megabytes L2 shared cache. So it's co-running with streaming benchmark. It's very much like the program 2 on the previous slide. So in this case, it joined the tile size in terms of reuse distance. So we're tiling, you see the range showing on the x-axis is really the L1 cache size. We are really tiling for the private cache. The black one shows the just tile without considering the peers. We see the best tile size. When we run this program by itself, the best tile size is actually very close to the private cache size, because there we get the maximal reuse. So after that, we get conflict misses. But then just right before that is the best tile size without program co-run. But when we run a stream program with matrix multiply, what we see is that the best tile size is actually much smaller. It's somewhere around 30 kilobytes. And then if we use the best tile size for the solo run, we actually will see 10 times as many cache misses. So that's clearly a serious problem. But can we factor these considerations to change loop tiling to consider the peers? So that's really make it defensive. And the way we model it, we look at the data usage. We say how much data are reused, and then how long it's being reused. And then the frequency of inclusion victim misses is depending on how fast the shared cache is actually being used by the peer programs. So as a result, the mic data would be evicted. So that's a measure we call survival window. So after every survival window, my reused data will be evicted from shared cache. So total number of inclusion victim misses is going to be computed by the active period divided by the survival window. That's how many times I will incur the inclusion victim misses, and then times the reused data, because all of these will be misses. So that's our model to compute the effect of inclusion victim misses, the effect of interfering. And the survival window is just figuratively shown by this orange square. That's really how often the data get evicted from shared cache because of the data access by peer programs. And this is a simple model, but for tiled programs actually seems correct. So there's a saying that all models around some are useful. So, but this one is useful, we have to test. And then, fortunately, before Bing came to Rochester, he worked with Shiming Liu, who really in charge of the half the Open64 compiler, so he really was trained by Shimin, and he knew how Open64 compiler implements the loop tiling. And then he chose the compiler as the basis, which is an excellent basis because Open64 has the best optimizer performance among the production quality compilers. So GCC, as far as I know, is no comparison. And then the other one is that loop tiling is only one of the transformations in the among other loop transformations. In Open64, it's called the loop nest optimization. So that includes not just loop tiling, but also loop fusion, loop distribution, loop interchange, anion gem, just a whole host of transformations. And then this excellent compiler was actually designed by Wolf, Maiden, and Chen, and others, and they explained how the compiler was designed in their 1998. It's really a compiler classic paper. And in the system, the interface for tiling is such that there is a formula to compute the number of misses for each tile size, and then the compiler it actually does a binary search to find the best tile size at compile time. And just a little bit explaining how the compiler calculates the number of cache misses. You compute the footprint for each loop. So here I'm showing the footprint for loop I and the footprint for loop J. And then you see it's parameterized by the tile, the block size, the B, BJ, and BK. And then from these footprints, the Open64 computes the number of cache misses. So by selecting the right BJ, BK, it tries to minimize these misses. But the original design didn't consider the case of sharing. And this is where our new model comes in. So the complete model is really showing here. CMJ is the cache miss for loop J. That's a formula that's from the Open64 compiler. So all we need to do is to say, in addition to these misses, you also have inclusion victim misses. And that's going to be computed by this simple extension for the formula. So once we add this factor into the original CMJ equation, then the compiler works just as usual. It just finds the block size and minimize the number of cache misses. But in this case, actually also minimize the number of inclusion victim misses. And then it does so in conjunction with all the other transformations. And so to test the result, we use Pluto benchmarks. It's really great to have this community that we can have the compiler, we have also the benchmarks, and then we use simulation and the real processing. For peers, we use the stream benchmark, which has the most aggressive shared cache usage. That's the extreme case. And then we also test the program co-run itself, so we call it symmetric co-runs. I'm only going to talk about the result with the stream benchmarks. And these are the simulation results. We're showing the different tiling tile program versions. So there is default tiling without considering inclusion victim misses, and then we also have a parameter. So we still have the problem that when we say interference, we don't really know which program will be running with this tile program. So we have a compiler parameter to say there's a defensiveness you can choose, and this is tied to the notion I explained earlier is a survival window. So if the program expects long survival window, then the defensiveness it doesn't have to be high. But if the program expects short survival window, then it needs to be really high. So the compiler has this defensiveness going from 1 to 8 as a compiler parameter. So here we're testing defensiveness 1, 2, 4, and 8. So these are 4 versions in addition to the default tiling. And then we're testing for 5 Pluto benchmarks. The miss ratio, simulated miss ratios are measured first for co-run with one stream programs, the other which is just solo run. So if we look at the bottom graph first, what we see is that because the tiling, it's being conservative, is choose a smaller tile size, and so to be defensive of the shared interference. As a result, we lose cache reuse. So you see slide, we see the increase in cache misses in solo runs. And in some cases, so it is actually for high, so defensiveness 4 and 8 is actually a lot increase as a result of being defensive. But maybe that's not the level we should choose. But if we look at the co-run, so in this case, really we see why we want to be defensive, because if we were not, the default tiling, which the number of misses will increase really dramatically. And when we run it on Nehalem x86 machine, this is actually testing with co-run with 1 stream, 2, and 3, in addition to solo run. We do see improvements. So the paper has the results for all defensiveness cases. Here I'm only showing you defensiveness of 4. And in this case, we see the improvement. This is the improvement over the default tiling. Actually was the default generated by the OpenCV4 compiler. But in the co-run cases, we do see improvements in almost all cases. And then the other study we did is, what about cache oblivious algorithms? So the premise of cache oblivious algorithm is that because we don't know what's the right tile size, and then let's tile for all possible cache sizes. Maybe that's the right solution for defensive tiling. So we tested, thanks to Qing Yi, we got the code she has from her paper in PODI 2000, and then when we run the code, so actually it doesn't have the tiling parameters in the code, but it has this recursion threshold. So with recursive matrix multiply, for example, you don't recurse all the down to the single element. You stop recursion at a certain level. So we tried all different thresholds. So what we found is that in some cases, actually, it's very good. So for co-run with 2, 3 streams, it recurs with threshold 16 and 32, we see a pretty large improvement compared to the versions, the base tiling that isn't defensive. But still, it's not as good as what we have from Bin's defensive tiling. So, some of the questions we are still studying. But to summarize, I think in CGO release, we're talking about compilers. In a sense, compiler optimization is making a program self-aware, so the program looks at the code. Now, what we want to do, I think, in the new environment is we need to be peer-aware as well. So in this case, we do show that at least for loop tiling, there is an effective way to reduce the interference and by considering the peer program. And then we still don't have results the effect of defensive tiling when co-run with other programs. And then also we would like to choose the defensiveness based on the ongoing environment. So really we want to measure the interference saliva window at runtime and then choose the right tile size. And also, we want to extend this to include other type of program transformations to make them peer aware.
Let's first thank our speaker, and we'll take some questions.
Questions? Minjo Zhou from College of William Mary. I have a clarification questions. Do you use dynamic information for this loop tiling technique?
Good question. This is so we thought about doing that, but then we didn't use any dynamic information. The whole transformation is static.
But I think the input size will be important for the loop tiling.
It has an effect when the input size becomes smaller than the tile size. So you can tile to be bigger than the data the program has. But once you're larger than the tile size, it really doesn't change the cache reuse. We just compute on each one tile at a time.
Other questions?
I'm Wu Xu from Institute of Computing Technology. Well, you have mentioned that as we don't know the Quran programs, so you set a parameter for the compiler to suggest the defensiveness level. So have you got any hint or automatically or partial automatically for the developers to set these parameters, because we don't know the Corona and we don't know how much or if the Corona is friendly enough, or they will compete for the cache very intensively. So any help for the developers to set this parameter?
Very good. This is exactly the next open question that we're studying, continuing this work. But what this work has done is to generalize the notion of interference. We're not hiding for specific peers. We have the generalized interference in terms of survival window. So at least that part, I think it's still a step forward.
Thank you.
Other questions? Actually, I have one, Shane. So the auto-tuners have done pretty good, with trying to figure out tiling. But one of their problems is they just take too long. And one of the things that you can try to do to help them is if they have a better model to kind of localize where they're searching. So I'm wondering, do you think your model could be, put into an auto-tuner as a way of kind of focusing where they're searching? Does that make sense to try to do something like that with your model? Because your model seems it's nice. And it's, nice and simple, and it seems to work well.
That's right. That's a really sort of fundamental, the interaction between modeling and the searching, and that trade-off is here as well. But for shared environment, I don't know how auto-tuning, it's certainly a new dimension for them. It's if they have to has to search the best tile size for every conceivable peer, that's not going to be realistic. So the model may help them.
Yeah, but you don't consider the peer already, right? And so, absolutely. You can't consider the peers because you don't know what they are. But in terms of just, the general auto-tuners and trying to figure out what the tiling are, again, what I've seen is they're pretty good, but they just take so long. And so it would be kind of a speed up for that.
I don't see this can speed up their search process, but I do see that if they use the notion of survival window, they can sort of put up the environment to have a different cache interference, so that instead of doing compiler tiling or the compiler choice of tile size, that we can actually search for the best tile size for each survival window. That's what I can see, that how this model may help auto-tuning. So coming back, auto-tuning may also help this, in that we may think this is the best tile size for this particular interference case, but maybe it's not. Maybe we should search and see if we're really correct.
Okay. All right, let's thank our speaker again. Great. Our next talk is from a group from